Arjun, thank you very much for an interesting presentation. So we'll take questions again. Who's brave enough? There goes.
Yeah, Michael Bihonik with Apache. Have you started playing with external environmental factors?
So I personally never looked at the external factors. I know that when they were starting this off, they tried many, many things to kind of get this working. And at some point, they had much more complex models that did take these factors into account. And what happens was that you can't query these models fast enough to do this kind of control. And so one of the key points about our model is that it's so simple that you can query it thousands of times per minute. And that lets you do that the receding horizon simulation every time step. And with those more complicated models, you just can't do that anymore.
I found the work you did. Oh, I'm sorry, Sarah Shayegi with Shell. I found your work very interesting. Also, some of the intermediate steps that you were doing. For example, you took all the errors and all the trajectories and then put them all in the same set, basically. And you were using the time warping phenomena. Was that just a standard algorithm, or did you do anything that was different for that?
It was fairly standard time warping. The only thing that you might say is different is the cost function that we use. The details of the cost function get a little bit involved, but the hidden Markov model that I described, you can, for each sequence of states in that model, you can assign a probability to it. And so the cost function for time warping essentially is some function of the probability associated with that sequence of states.
Okay.
But the algorithm itself is actually just kind of completely off the shelf. It's probably 40 years old at this point.
And do you think that's going to be, what I'm thinking is taking this kind of information and going to the drilling, for example. So would you think, because what you're doing is you have data that is going to be the same pattern, but in a different time sequence. So do you think that kind of algorithm, is it a robust, reliable algorithm, and it would be useful for this kind of patterning and putting it all in the same time steps?
Yes, I think so. I think you'd have to kind of figure out the right cost function, but that algorithm, I think, is very robust. As soon, you've got to put a little bit of thought into the cost function, but that's probably one of my favorite algorithms, actually. And I think it does a great job if you give it the right input.
Well, great job. Thank you.
Thank you.
Walt Aldred from Schlumberger. That was a really great presentation. If we go back to Bertrand's presentation, it looks like what you've done is you've picked the mind of the pilot, the human operator, to be able to do that, and then you take in the best of the best that he can do. And Clay said, well, robots and automation is all about then progressing beyond what humans can do. How do you see your approach taking that challenge on? Is it possible? Do we need another approach to get the best out of the machines and the best out of the humans?
So I think it really depends a lot on the task that you're trying to do and how you kind of define what's better than what a human can do, right? So in this case, the computer can repeat the same maneuver very reliably, and a human can't do that. And if you think that's superhuman performance, better than a human can do, then that's one way of thinking about it. At the same time, if you just took that trajectory and compared it to what a human flew, it's very similar. So maybe you say that it's not actually doing better than what a computer, it's not actually doing better than what a human can do. And it's just very task specific. And so I don't know if the right way to think about it is exceeding humans or not. Another way of thinking about it is that with humans, maybe 1 out of every 100 times they reach maximum performance, right? And so that's what you want to be focusing on. And maybe you really need to go beyond like superhuman performance in those cases. In other cases, we've actually looked at, for other kinds of work, trying to speed things up. And so one of the other projects that we've used these apprenticeship learning techniques in is surgical robotics. And the project that I'm thinking of right now is trying to get a surgical robot to autonomously suture. And the technique we tried there was we took demonstrations provided by students in the lab. So these aren't experts by any means. And what we did is we sped them up, essentially. It's not quite as simple as speeding them up. There was a structure to it. But in the end, we got better sutures than what the lab students could do. And can we do better than surgeons? It's hard to say because we don't have those demonstrations. But we do have ways of trying to improve them, and it's really all about defining what an improvement is.
Yeah, so a lot of what I was thinking about there was, I mean, you mentioned some of them. Repetitive things, obviously your technique will work for that. Speeding things up, it could possibly work for that. There are sort of highly synchronized things that drillers can't do, you know, like changing the flow and RPM at the same time and things like that, that really take what a machine can do and then take it to the next stage. So you're right, there's a whole task-specific set of things.
Right, and I guess if you want to describe the task to me a little bit more, either afterwards or whenever, then I can try to think about it a bit more, but it's just hard for me to say without actually getting some more details.
Charles Piper with IDE. Have y'all tried, or in your research building up to this, did y'all try implementing predictive modeling instead of actually taking the measurements from an active pilot?
Yes. The example I showed you where it crashed was kind of that idea.
Do you have more to add to that?
I mean, yeah.
Dave Moran with Schlumberger. In your process of interpolation where you're redesigning the kind of filling in the blanks in your trajectories, were you using a linear method to do that or some type of neural processing?
Actually, it was just an extension of the method that we were using to generate the hidden trajectories. And so, like I said, it's a probabilistic inference thing where we have these demonstrations, and the algorithm is essentially trying to find something that's close to all of the demonstrations. And so the way we did the parameterization was we gave it those 5 demos, the 20, the 30, the 40, and the 50. And then we inserted something that was a kind of a fake observation that biases it towards what we want. Right? So what we want is a 25-meter tall stall turn, and we have a 20 and a 30. And if you just gave it those demos, okay, so maybe that's a bad example, because if you had a 20 and a 30, then maybe it would average out to 25 anyways. Let's say you gave it the 20 and the 50, okay? And you want the 25-meter stall turn. So if you just kind of gave it to the algorithm, it might generate something that's somewhere in between that. But we want it to be 25, or as close to 25 as we can get. So we feed it an extra observation that didn't actually happen, and force it to bias it to be closer to 25, while still obeying the dynamics of the helicopter. And so that's the key thing here, is that our probabilistic model still takes the dynamics of the helicopter into account. So it tries to find something that's close to the demos while still taking the dynamics into account.
Just to follow up, how did it do when you projected outside the bounds of your training data?
That depended a lot on the maneuver. And so for stall turns, it actually worked pretty well. And for loops, if I recall correctly, it didn't work that well. And so maybe there's some more analysis to be done there about what exactly you should do in those cases. But I don't have a good answer off the top of my head.
Hi, Carl Appleton with NOV. Did you fly your scenarios on gusty days, or were they all totally calm?
They weren't all totally calm. Obviously, the best performance was on days where it was totally calm, but it actually still works reasonably well on days where it wasn't. Or if the wind would gust up, it would actually still do well. I mean, it would essentially add a bit of a drift, and so the entire trajectory would maybe be off by 3 or 4 meters more, but it would still look the same. It's essentially as you just offset the trajectory. And so it does pretty well. The one thing that's very important is that the demonstrations are collected on clear days, but the execution will still carry over to windier days.
If you had a parameter of different gusty days, so some very extreme and some less, would you be able to come up with a scenario that would fly robustly?
I think so, but I'm not really sure if you need more sensing to do that, or if it would just be as simple as kind of having a few different modes. I guess it depends on what exactly you're looking for. If you wanted to fly within that 1 to 2 meter error range, regardless of the conditions that everything was collected in, and regardless of the conditions that you're executing it in now, I think you would need more sensing on board.
Thanks.
Anyone else to pose a question? Hey, Arjun, you had a conversation with Hani about drill string dynamics. What did you get out of that conversation?
So I think the key thing for trying to take this and apply it to drill string dynamics or anything in this field is essentially the data. And with helicopters, it's fairly easy to get data if you have a good pilot. And it was a lot less clear to me how easy it is for you to get data and how easy it is to get kind of repeated demonstrations. And so what Hani mentioned is that they're trying to build up a library of how different drill bits interact with different materials and all of that, trying to come up with this library of data such that they can simulate reasonably well how different drills react in different environments. And I think that's a good step in the right direction. It's a bit less clear to me on exactly how much data is necessary for this case, just because I'm not as familiar. But yeah, the data is key, I think.
Any more questions?